Today we are going to talk about some of the work we did in our research group at the University of Toronto and also in collaboration with Intel in the context of the Crossroads Center. And this work is basically about how we do architecture exploration for novel reconfigurable devices that we're starting to see in products now. To just quickly motivate why we are doing this. So over the past 30 years, we have seen FPGAs kind of like evolve from simple 2D grids of programmable logic, routing, and IOs into more complex heterogeneous devices that contain different blocks like digital signal processing blocks, embedded memories, hard memory controllers, PCIe controllers, and even complete processor subsystems embedded in the FPGA. So they're becoming more complex and more heterogeneous. And more recently, we have seen products from FPGA vendors that go beyond FPGAs. So for example, there's the Xilinx Versal device, which consists of an FPGA fabric, a bunch of ARM cores that are general purpose in software programmable, and a bunch of vector processors on the side that can be used to accelerate any parallel application and most prominently AI applications. And all those system components are kind of hooked up over a system level NoC that handles all the system communication very efficiently. Similarly, at Intel, very recently, we saw this Intel Agilex M device that also incorporates a network on chip that interfaces external memory like HBM and helps you distribute the HBM bandwidth efficiently throughout the FPGA fabric. And you can also think of future devices that we haven't seen in products yet, but with maturing 3D integration technology, you can see the future of integrating an FPGA fabric on top of an ASIC-based die that incorporates all sorts of functionalities that we need in a reconfigurable device. So we tried to basically give a name to all those devices. So we call them reconfigurable acceleration devices, or RADs. And if you look at the design space of those RAD architectures, we would be able to identify three main kind of like components of those devices. So the first component is the FPGA fabric. And in order to do architecture exploration for that, we need to answer questions like, how would the routing fabric of this FPGA look like? What type of logic blocks should we have on it? What type of hard blocks should we embed in the programmable fabric? And also, what's the effect of changing this FPGA architecture on the FPGA CAD algorithms? And then the second component are kind of the coarse-grained accelerator blocks that can be either embedded like beside the fabric, something like the AI engines in Versal, or maybe in a base die in a 3D integrated device. And we would need to answer a few more questions about the architecture of those accelerator blocks. So things like, what functionality is worth hardening in those accelerators? What is the granularity that we want for those blocks? How many of them? And also, more importantly, how do we program those accelerator blocks? And then the final component is kind of the system level interconnect that hooks up the FPGA fabric with those accelerator blocks. So we need to look at the network on chip specification, what type of abstraction is presented to the user, and also having a NoC embedded in the FPGA fabric creates a very interesting FPGA CAD problem, which is the NoC placement, because now you have those different application modules on the fabric that you can place on different parts and hook to different routers of the NoC. So we also need to think about the CAD implications and how to do the NoC placement in that context. So once we combine those three components together, we find out that the design space is huge, and we need to answer all those questions and figure out the interactions between each design decision of those three components to the other design decisions that we take. For the past, I don't know, 20 or 30 years, we have been doing FPGA architecture exploration. So we know how to do this, and there are already FPGA architecture exploration flows out there that researchers typically use to evaluate new FPGA architectures. If some of you are familiar with the VTR flow, basically what you do is that you describe an FPGA architecture that you want to evaluate, and then you write a bunch of benchmarks typically in HDL, Verilog or VHDL, and then you run it through the VTR flow, which does the magic of mapping those benchmarks written in HDL to the candid FPGA architecture, and tells you, okay, here's the area of this FPGA, and also here's the clock frequency that you can basically run this circuit at. So if we look at those conventional FPGA architecture exploration flows, we find that we write benchmarks in HDL, and at the end, we get application agnostic performance in the form of clock frequency and tile area of the FPGA. And in order to make sure our benchmarks are functionally correct, there's no way of doing that except RTL simulation. And the CAD tool, the VTR flow, is routing wires between different blocks in your netlist. And if we try to look at those characteristics in the context of the RAD design space exploration, we'd find that if we write the applications in HDL, this kind of poses a bottleneck for the application architecture co-design, because when we are building those RADs, we don't really have applications to run on them. So you kind of do a process of application architecture co-design, and if we need to do that in HDL, it becomes very tedious and labor intensive. And in the context of a RAD, the Fmax of the FPGA or the circuit implemented on the FPGA is not enough. We need to look at the bigger picture of like how all those system components interact together to get an application-specific performance metric. For RTL simulation, if you do RTL simulation for the complete RAD device, you would find that you need to develop a ton of HDL infrastructure, things like the NoCs, the routers, all the hard accelerator blocks that you want to embed. So you need to develop a lot of infrastructure, and it will also be very slow to evaluate those RAD architectures on the level of RTL simulation. And finally, the conventional architecture exploration flows have no notion of routing packets or no notion of a NoC embedded in the device. So this is also problematic. So that's why we need to develop new RAD architecture exploration flows that have a higher level of abstraction for applications, can give us application-specific end-to-end performance in the form of like cycles, the number of cycles that you need to execute a specific application. We need this simulation to be high level and fast enough to enable fast turnaround time for exploring the huge design space of RADs. And we also need the exploration flow to understand concepts like system level NoCs and other hard blocks in a RAD. And that's what we try to do in our RAD architecture exploration flow. So I'm quickly going to give you an overview of the complete flow that we are building. So the first component is RAD-Sim, which is going to be the main focus of what we talk about today. And RAD-Sim is basically the system simulator. It takes as inputs SystemC description of your hard accelerator blocks and application modules that are implemented on the FPGA. It also takes some architecture parameters, network on chip specifications, and module assignment, which is the assignment of application modules in the FPGA fabric to specific routers. So you can think of it as the solution to the NoC placement problem specified as an input. RAD-Sim takes all those things, stitches them together, and performs cycle level simulation of your application on the RAD instance that you describe, and produces as an output things like NoC traffic patterns, the end-to-end application performance, and it can also do functional verification if you supply it with a set of vector test inputs and their golden outputs. And this is built to be fast and enable fast turnaround time, so you can simulate many different RAD instances that you're trying to explore. And once you're happy with a specific instance, or you have a few candidates that you want to evaluate even more in more detail, you move to the second stage of the exploration flow, which is the implementation phase. So at that point, we can write a set of RTL descriptions for the accelerator blocks and the system modules that we have in our RAD. And RAD Gen, which is the second component of the flow, will take this, pass it through an ASIC flow, and give you results of the implementation results in terms of silicon area, frequency, and power of those components. So you get a sense of how expensive would it be to implement those blocks in a RAD. And on the other side, it takes the application modules that are supposed to be implemented on the FPGA fabric, push them through an enhanced FPGA CAD tool, and give you the implementation result for that. And you can think of this enhanced FPGA CAD tool as the CAD tool that does the classic placement and routing of those application modules, but also does the network on chip placement, decides where to place those application modules relative to the NoC. And you can see very interesting relations between this CAD tool and RAD-Sim, where the CAD tool can, for example, propose a specific NoC placement and then invoke RAD-Sim to evaluate it on an application level to see if it meets latency constraints or performance targets or not. And this is kind of like analogous to static timing analysis in the classical sense for normal FPGA place and route. So in this presentation, we're going to be focusing on RAD-Sim, which is developed, published, and open sourced. I'm going to give a link to the GitHub repo at the end of the talk if you would like to check it out. So focusing more on RAD-Sim, as I mentioned, it gets some application-related inputs, which are the application modules to be implemented on the FPGA fabric, and the module assignments to NoC routers, and some RAD architecture-specific inputs, things like the accelerator blocks that you want to have in your RAD, some architecture parameters and NoC specification, and then it produces the NoC traffic reports, the end-to-end application performance, and verifies the functionality of your application if you want to do that. So it's fully developed in SystemC, which basically has two advantages. The first advantage is that it's much faster than simulating it in RTL, which we need when we kind of try to evaluate this like very complex heterogeneous devices. And SystemC also enables designer to define those accelerator blocks or application modules in different levels of abstraction. So you can have something that is more of a behavioral description of the module, or closer to RTL level description, but written in SystemC. And this helps you trade off between the faithfulness of your model and the designer productivity. How long would it take you to write the SystemC description of those blocks? Behind the scenes, RAD-Sim uses Booksim to do a cycle accurate NoC simulation. So we don't have a NoC model, we actually simulate the NoC transactions. And Booksim is kind of the to-go simulator for studying NoCs. And besides that, RAD-Sim provides infrastructure components and telemetry utilities that help you basically probe into the implementation of your application on a RAD, identify bottlenecks, and kind of like facilitates your exploration of the design space. So if we quickly introduce like Booksim, which RAD-Sim uses to simulate the NoC. So as I mentioned, this is very widely used in the academic community to simulate NoCs. It's heavily parameterizable, contains a lot of off-the-shelf topologies, routing functions, router microarchitectures, and other NoC components. So it allows studying a wide variety of NoCs. And it's also built in a way that makes it very easily extendable if we want to support more feature than what's currently supported in Booksim. What I'm showing here is like how Booksim is implemented. So Booksim is only focused on simulating the NoC from a performance perspective. So it generates a traffic generator around an NoC, starts injecting traffic at different nodes, and then you get a sense of what type of performance you can get out of this NoC. And the thing I'm showing in the middle here is just an example of how parameterizable it is. So you can define different parameters related to the topology, the routing functions, the type of router microarchitecture you would want to use, and also the different delays of different parts of the NoC. So very parameterizable, which is very powerful in the context that we want to use it for. So this is a great starting point, but it's not enough. We need to add some missing feature to be able to use it in our RAD flow. So the first thing, we need to wrap Booksim in a SystemC wrapper to be able to integrate it easily with the different RAD modules. We also need to have content tracking for the packets because we want to also verify functionality of our applications. So we need to have the bookkeeping of the actual data injected at a specific node and ejected from another node. We also need to implement some NoC adapters, which would be used to, you can think of the adapters as just the highway ramps of getting from the accelerator blocks or the FPGA fabric onto the NoC to be able to experiment with different user-facing abstractions. So there's just a brief idea of what we mean by a NoC adapter. So we actually implement SystemC NoC adapters that follow the AXI streaming and AXI memory mapped protocols. So right now in RAD-Sim, the user can just hook up any module that abides to an AXI interface. But we also build this in a way such that if you want to experiment with other protocols, you just need to implement your own adapter and plug it into RAD-Sim to be used if you want to experiment with something other than AXI. And what the NoC adapter really does is that it interfaces with single or multiple AXI logical interfaces. So you might think of different AXI modules trying to hook up to the same router. This goes through a layer of abstraction and muxing, then whatever transaction is selected gets packetized and then injected into the NoC. So this is one side of the adapter. On the other side, you can think of the same steps, but in reversed order. You eject flits, you depacketize them, and then you present it to the intended logical interface as an AXI transaction. So all the internal stages are kind of like transparent to the user. And the way we build those adapters, that as I mentioned, it enables multiple AXI modules to basically connect to the same router. So it provides this arbitration mechanism between different interfaces. And we have some arbitration mechanisms implemented, but you can also implement your own arbitration mechanism, for example, and just point RAD-Sim to use this mechanism. And the adapters also support like multiple clock domains. So you can think of parts of those adapters running at different clock speeds, depending on whether it interfaces with the fabric or a hard block. And this helps us experiment with kind of the boundary between hard logic and soft logic when it comes to interfacing with the FPGA fabric. On this slide, I'm just showing examples of RAD-Sim inputs and outputs to give you a sense of what would you give to RAD-Sim as an input and what you expect to get as an output. So you can see there's like many parameters. Those are just a subset of the parameters. You can specify things related to the NoCs, how many NoCs do you have in your system, different NoC parameters, different parameters related to the NoC adapters, and also parameters related to the modules that you hook up to the NoC. And what you expect as an output, so RAD-Sim has some telemetry utilities that basically can collect simulation traces, and then we have graphing scripts for those. So for example, what I'm showing here in the upper graph is an example output of RAD-Sim that shows the unloaded latency of communication on a 4x4 mesh network. So you get the number of router hops that you go through and also the latency in nanoseconds, and you can look even deeper into this latency and kind of break it down into different components. How much time do you spend in the adapters versus how much time do you spend in the app going through the actual NoC. This is just a sense, but for the rest of the presentation, you're going to see other sets of results and simulation traces that we can collect using RAD-Sim for specific test cases. So now I'm kind of like going to switch gears a little bit to show you an example of what we can use RAD-Sim to do. And basically by taking a case study that we did from an application from the AI inference domain using the NPU. So first, let's maybe talk about the NPU. So the NPU is the neural processing unit. It's an FPGA overlay architecture that is targeted for AI inference and specifically for the kind of AI models that are more memory bound. So things like multi-layer perceptrons and sequence models like RNNs, LSTMs, and GRUs. And when the NPU started, it was a replica of the Microsoft Brainwave architecture. We tried to reverse engineer like the missing details from the Microsoft ISCA paper and try to replicate the architecture to our best ability. But then later on, we took this architecture and migrated it to newer AI optimized FPGAs to gain much higher performance than what Brainwave could achieve when it was published. So this overlay architecture is a VLIW soft processor, and it basically follows two key design philosophies. So the first one is to amortize control. So those instructions are very expressive. So a single instruction can actually trigger the execution of thousands of operations. I think for the instance of NPU that we use, each instruction can trigger up to 45,000 multiply and accumulate operations. And the other philosophy is that you customize the memory subsystem, exploiting the FPGA reconfigurability to basically make use of the tremendous on-chip bandwidth between the BRAMs and the compute units on the FPGA. So the NPU consists of 5 coarse-grained functional units that are chained together. So the first one is a matrix vector multiplication unit, focuses on doing the kind of the tensor operations, does the bulk of computation, and consumes most of the FPGA resources. This is followed by some modules that implement vector element-wise operations, and finally a vector load store unit that can take the result of this pipeline and write it back to any of the architecture states of the NPU. So really there's massive compute parallelism going on here. The functional units are very coarse-grained and the instructions are very CISC-like in some sense. You write the RTL for the NPU once, you carefully tune it to your target FPGA to generate a single very high quality bit stream. You deploy it on the FPGA once, and then you program it to run different models purely through software. So we have an NPU front end that accepts TensorFlow, Keras descriptions of your model, compiles it down to NPU instructions, and ships it to the FPGA to run those instructions on the NPU overlay. And just to give you a sense of like the kind of like enhanced version of the NPU that we did for the Stratix 10 NX, it's Intel's AI optimized FPGA with tensor blocks embedded in the fabric instead of DSP blocks. So we do this study and we compare the NPU on Intel Stratix 10 NX to its equivalent AI optimized GPUs, so same process technology, the V100 and the T4 GPUs. And really the fair comparison between those two is T4, which is closer in die size to the Stratix 10 NX. But we also include the V100, which is a monster, much bigger die size than the Stratix 10 FPGA. And this is showing the performance across different benchmarks of MLPs, RNNs, GRUs, and LSTMs. And we show that the NPU on Stratix 10 NX can get about an order of magnitude better performance than those AI optimized GPUs, and a similar benefit in terms of energy efficiency. So this is just for the compute kernels, but we also, if you're interested about this, you can check out the paper. We have a study for the end-to-end system where you put the GPU, you plug it as a PCIe card in a host CPU, and you communicate with the FPGA over an Ethernet interface, and we measure the end-to-end system performance. And we show that the benefits of using the NPU on Stratix 10 NX is also really big when you focus on the system level performance, not only the compute kernel. So kind of the summary of what I mentioned is that the NPU is a state-of-the-art application from the AI inference domain, very high performance and an order of magnitude better than GPUs for those workloads. And what we want to do through this case study is to take this NPU, migrate it from a normal FPGA to a RAD architecture, and then use RAD-Sim to evaluate its performance and figure out what are the performance bottlenecks, and kind of do some sort of an architecture application co-design of a new RAD device. So the first step was to create a baseline SystemC model of the NPU. So we take this architecture that I just described, we write a SystemC model for the different blocks, and then we compare it to the RTL that we have for the NPU. So our SystemC model, I'm just showing here to basically show that the SystemC model can model the NPU performance with very high accuracy. So the average error is about 5%, but it's actually much, much faster than simulating it in RTL. It's about 26 times faster and accurately models the performance of the NPU. Once we have the SystemC model of those blocks, we need to look into how can we integrate it into RAD-Sim and use it with an NoC. So in order to be able to use it with an NoC, we need all the NPU modules to be latency insensitive. So actually the baseline implementation has most of the modules being latency insensitive because there are those elastic FIFOs between different coarse-grained function units. But there are still some links in the baseline NPU that are still latency sensitive. So for example, the bulk of the NPU logic and computation happens in this matrix vector unit. And it's likely that we need to kind of like break it into smaller tiles in order to be able to utilize it in a RAD with an NoC. So those links between different tiles in the MVU, for example, are latency sensitive. And also there's a write back and hazard detection and resolution mechanism that is also latency sensitive in the baseline. Those are just two examples of latency sensitive links in the application that we are targeting. So we start trying to get rid of those latency sensitive links to make the NPU more modular and ready to hook up to the NoC. So once we do that for the write back pass, we lose about 9% of the NPU performance. And then once we do that for the tile as well, we lose another 8%. So not drastic loss in terms of performance, but it is the performance is affected by those minor changes to make them latency insensitive. And then the next step was basically to start integrating it into RAD-Sim and hook it up to the NoC. So what we do is that we build AXI streaming wrappers around those modules. And those wrappers basically decouple the compute and communications of those modules. So you can specify different link width for those AXI streaming wrappers, which enables us to easily hook it up to a NoC later on in RAD-Sim. And the first experiment that we do is that we assume there's an ideal NoC. So each module is hooked up to an exclusive router interface, and this router has no arbitration. It just goes directly to the destination module. So it is basically the best case of an NoC. It's an ideal peer-to-peer interconnect. And once we do that and we give the NoC interfaces the full width that those compute modules need, it doesn't lead to a huge performance degradation. It's only 3%, and those 3% is basically the cost of adding the AXI streaming wrappers for those modules. But then once we limit the width of those interfaces to realistic NoC router interface width, so for example, 512 bits, which is the case in the NoC Versal, the NoC in the Versal device, or other academic studies for FPGA NoCs, we actually find that the performance falls off the cliff. So limiting the bandwidth actually kills the NPU performance, even if we assume an ideal peer-to-peer NoC with no traffic congestion on the NoC. And basically what I want to show in the next few slides is that RAD-Sim will help us identify the design bottlenecks and basically quickly experiment with solutions for those bottlenecks and evaluate the effect of those changes on end-to-end performance. So once we got this result of like the performance falling off the cliff because of bandwidth, we started looking at the NPU from an application perspective. So there's just a graph representation of the different NPU modules and how they communicate with each other. And then we start annotating those graph edges with the bandwidth of interfaces going between those modules in the baseline NPU. And you can actually see that some of the buses are really wide, so up to like 7K bits between some modules, and the smaller buses are even unreal, like terribly wide. It's like 2,560 bits for each one of those buses. So because of the massive parallelism that we have in the NPU, this results in wide buses. And it was okay to implement this on the FPGA fabric because we have a lot of programmable routing that we can basically drag wires from whichever place on the FPGA to another place very easily. But once you think about hooking it up to the NoC, now you're kind of like limited to a specific NoC interface, for example, that you need to abide to. And we started thinking about this structure of the NPU, and there's actually no real reason for this granularity of the NPU modules. We just inherited this granularity of modules from the baseline design. But if you think about it, most of those modules have independent SIMD lanes, for example, so you can kind of like restructure them and replicate some of the register files to basically break them down into smaller modules and manage and distribute them even more and manage the output bandwidth of those different modules. And this is what we do in RAD-Sim. So we basically take those like MVU tiles, we break the SIMD lanes down, we replicate register files, and then because those local interconnects between tiles and accumulators were very wide, so we localize those inside of a module so they don't have to hop on the NoC. And then we do the same thing for the vector element-wise operations, also split the SIMD lanes and localize the wide buses. And for the loader, there was a single loader that writes back results to all the different modules. But actually, some of those modules operate at lower precisions than others. So we're kind of like wasting some of the write back bus. So why don't we have like different dedicated buses that communicate to the high precision module versus low precision modules? So a lot of details here, but really the high level message is that we needed to look at the application that we took for granted from an FPGA baseline implementation and look into how can we make it more distributed and manage the output and input bandwidth of those different modules. And once we do this, we have very manageable bus sizes between the modules that need to hop over the NoC. And this is what we call like bandwidth-driven approach of restructuring the NPU to be ready to be hooked up to a NoC. And all this restructuring was driven by, we run a RAD-Sim simulation, we look at the bottlenecks, and then we start like changing the design rapidly in SystemC and simulating again, and so on. So this kind of like highlights the power of the tool that we are trying to develop here. So this is kind of like the SAT curve that I showed before. We're starting from the baseline on the S10NX FPGA. We try to make the NPU more modular and ready for migrating into a RAD. And we start losing performance. And at this point, when we limit the interface, we realize that migration of the application as is from an FPGA to a RAD will not work. Then we do the bandwidth-driven design approach to restructure the application and distribute it into finer granularity modules and hook it up to different communication interfaces. So we regain a lot of this performance. And by restructuring the application, we also get some architectural choices. So for example, if we just increase the NoC interface from 512 bits to 640 bits, which is not a drastic increase, we can even get higher performance than that. So this kind of like shows the need for doing application and architecture co-design. You need to look at the application and reason about it when trying to migrate to those RADs. Okay, so all this was assuming an ideal NoC. So what happens if we take that and we introduce an actual NoC? So we introduce a normal mesh NoC, and this step would basically incorporate the congestion and the traffic patterns between different modules and incorporate this in the overall performance. So again, showing the baseline on the SystemX FPGA, the best we could get was bandwidth-driven design using an ideal NoC. And at this point, it was about 20% less performance. And this is the effect of having the latency insensitivity and some write-back bandwidth limitations. But once we introduce the mesh realistic NoC, we lose another 10% of performance. And this is an artifact of the higher latency of going through the actual mesh NoC instead of peer-to-peer connections, and also the effect of different communication patterns going through the NoC, which can cause some congestion at specific routers and induce more delay. So at this point, we were curious to see, like, why did we lose this 10% of performance when we included the realistic NoC? So we looked at some simulation traces dumped from RAD-Sim. So this is for the different NPU modules over time, showing the micro operation instruction issue and retire of those micro instructions. And we can basically see that the matrix vector unit, which is the bulk of the NPU computation, a very expensive module, is often left idle. And this is an artifact because the NPU runs AI models that have like dependencies across time steps, for example. So the NPU would remain idle until the output of the first time step goes back to the NPU, and then you can compute the next time step, for example, which causes this idle gaps in the NPU execution. And once you introduce a realistic NoC with congestion in it, this latency kind of becomes longer and causes degraded performance because of this idle gaps. And then we thought, okay, so we can actually keep the NPU busy, but by interleaving the execution of different models at the same time. So you execute the matrix vector operations of a model, you send it out to the other modules, you switch to a different model. So you can think of it as the NPU being multi-threaded. So it has multiple threads running different models and switching between them. And then the cheap vector operations, we can replicate those on the FPGA fabric, for example, and basically allow each set of those vector element-wise operations to be responsible for a thread of the NPU. And by doing that, we can see in other RAD-Sim simulation traces, when going to 2 threads and 4 threads, we can make better use of the matrix vector unit that we have and increase the overall performance. So we were losing an additional 10% of performance when we put the realistic NoC, but once we add a second thread or 4 threads, we actually gain back those performances at the cost of replicating those cheap vector element-wise operations for different threads of the NPU. So really, this gave us the insight of the expensive module, try to keep it busy, cheaper modules replicate in order to match the output of the expensive module. So this was still assuming a conventional FPGA with a mesh NoC. What about those more complex RAD devices that I was talking about earlier? So we use RAD-Sim to evaluate 3 different styles of RAD. So the first RAD that we evaluate is actually a simple one. It's 2 FPGA fabrics and that have like an NoC going in between them. And you can think of this as a conventional 2.5D integration technology, where the NoC links between the devices are the only wires crossing from one die to another over the interposer. The second RAD is something quite similar to the Versal style architecture. So there's an FPGA fabric and a side complex of accelerator blocks. And in that case, we choose the accelerator blocks to be matrix vector tiles that we use in the NPU. So we harden kind of like the fixed part of the computation, and then the vector element-wise operations can change on the FPGA fabric. And again, the only way to communicate between the accelerator blocks and the fabric is the NoC. And then finally, a more complex 3D integrated RAD, where you have an FPGA fabric on top of a base die, and the base die is full of matrix vector multiplication engines. So the message I'm trying to show here is that RAD-Sim can capture a wide variety of those RADs. So we can capture the kind of the big picture of the design space that we have, and we can also tune the low-level architecture parameters that have even different variations of each one of those RADs. So when we try to explore this big picture, so I'm showing here the relative performance compared to the Stratix 10 NX FPGA. And when we migrate the NPU to work on those two FPGA fabrics over the NoC, actually gain only 10% of performance. And the reason for that is that we don't use both FPGAs to do the full NPU computation. We use one to do the matrix vector element-wise matrix vector operations, and the other one to do vector element-wise operations, and scale out the vector element-wise operations to support multiple threads of the NPU. So I'm really saying that we are not making the best use of the two FPGAs. We are just simulating an instance of a RAD where we decide to do the implementations this way. And then the second RAD, which makes use of the hardened matrix vector units and gain about 30% additional performance compared to the pure FPGA implementation. And then once we go to the 3D integrated device, we gain a huge boost in performance because by moving all the matrix vector tiles to the base die, we can actually implement multiple NPUs on the same device. And then the huge bandwidth between the two dies makes it a lot easier for the MVU tiles on the base die to communicate with the vector element-wise operations on the FPGA fabric. So again, the message here is that RAD-Sim can help us explore the big picture of those different RADs, but it can also help us fine-tune some architecture parameters. And what I'm showing here, for example, is a very, very specific architecture parameter. So it's the buffer size of the virtual channels of the NoC of the RAD. Okay, it's a very specific low-level architecture parameter that you can think of it as a knob, and we can start like sweeping this architecture parameter and seeing the effect on performance of end-to-end applications. So what I'm showing here is the performance of different models, AI models running on the second RAD instance here, this one. And by changing the virtual channel buffer size, we can see the effect on performance. So as an architect, you can look here and say, okay, it seems like beyond a virtual channel buffer size of 8 words, we don't gain any much performance. So this might be a sweet spot for our architecture parameter. So yeah, what I'm trying to say here is that it doesn't only capture the big picture, it can also help us fine-tune those low-level parameters and see the effect on an end-to-end application. Okay, so I think this is the end of what I have. And just the key takeaways is that if we want to design those novel RAD devices, we will need new architecture exploration tools. And this is what we try to do with this RAD flow. And specifically for RAD-Sim, you can describe the applications at a higher level of abstraction and then quantify the effect of your design choices on the end-to-end application performance with faster turnaround time. You don't have to go through RTL simulation. And it also supports concepts like system-level NoCs and hard accelerator blocks. And then I showed this case study of migrating the NPU from conventional FPGA to a RAD. And we showed that RAD-Sim can give insights on how you can restructure or redesign your application to be better suited for RADs. So I've shown 2 examples for that, the bandwidth-driven design, and then multi-threading the NPU to be more suitable for NoC communication. And then RAD-Sim can capture a wide variety of RAD instances. You can think of monolithic RADs, 2.5D or 3D integration with different NoCs and accelerator blocks, and can also quantify the effect of those low-level architecture parameters on the end-to-end performance. And the example that I showed is virtual channel buffer size and how it affects AI inference performance. Yeah, so that's all what I have. The QR code and the link point to the GitHub repo for RAD-Sim if you want to check it out. And